Chapter 6 is about polynomials. We're going to remove the glass ceiling of keeping powers of x below 2 or 3. So in the past we've looked at constant, and that was x to the 0 power, and it's just a flat line. And then we checked out linear, and so then that kind of gives some angle to the line. We looked at quadratic, so that gives it the well-defined U-shaped curve. We've seen cubic in passing, kind of has that snake-like feature. And then we're also going to look at quartic, so the base variable to the 4th power, and then quintic, a variable input raised to the 5th power. But in all of these 0 through 5 powers, the variable is a base, and so then you get these characteristic graphs. In the future, we'll start messing with where the variable goes. So for example, exponential, the variable will be in the exponent, and then it'll give us a totally different looking graph. So this chapter is all about polynomials, and so that is going to be still a variable base, but raised to a variety of powers. The building blocks of polynomials are monomials. So the first kind of note card that you might want to make for this chapter is, what are monomials? They are a number, they are a variable, or they are the product of the two. To put it the other way, they cannot contain variables in denominators, so 1 on x is out. That's a special type of hyperbola that we'll get to later. They cannot have exponents that are negative. So that would be like x to the negative 1st power, because that is the same thing as the first one. I'm just trying to be extra clear here. And they cannot appear under radicals like this. That would look like half of a parabola on its side. That's the inverse of a quadratic, because this is the same as having an exponent of 1/2, so you can't have fractional exponents, you can't have negative exponents, and you can't have variables in the denominator. So basically you have to have a variable as your base raised to a integer exponent. That is going to sum up polynomials for you. And don't forget that you can have many variables raised to their own kind of exponent that is in the element of integers. And I just realized that not integers, got carried away, whole numbers. We can only let these be 0 or positive. So commit these rules to memory, and what I'm going to do next is, on the side here, write 7x, and now think about it. Should that be a monomial or a monomial? Pause as needed. This should be a monomial because it is the product of a variable and a constant. How about 2 on m to the 5th? Again, pause if needed to go through the rules. This is not a monomial because we have a variable in the denominator. This could be rewritten as 2 to m to the negative 5th power, and so we have a variable with a negative exponent, which a monomial cannot have. Let's take a look at the cube root of y. That's not a monomial because we have a variable as a radicand. You cannot have a variable underneath a radical. 2x plus 4. It's not a monomial because it is the sum of monomials, and the only operation that's allowed is multiplication. This would be known as a linear binomial. So bi meaning 2, and here we're just classifying monomials, single terms joined by multiplication. X to the negative 1st power. Yep, not a monomial, negative exponent. Y squared. Well, that's just a variable times a variable, and we have an exponent that's positive, so this is going to be a monomial. And the exponent was not a fraction either. 19. Just a constant, so that's a monomial. 4/3 x squared y to the sixth. Think about that one for a moment. It's a monomial because it is the product of variable bases with whole number exponents. It's okay that the fraction in front is a constant multiplied. And last one, A on B. That's not a monomial. You have a variable in the denominator. So now that we know what monomials are, we could start picking out characteristics of them. So the first thing that I want to talk about is the degree of a monomial. And basically the degree is a way of saying the maximum number of answers. Because when you see a variable, you're trying to figure out what it is, and that represents an unknown that you're trying to solve for. So the degree of a monomial, this is specifically of a monomial, it equals the sum of the variable's exponents. Not the exponents of constants, because remember the degree is trying to figure out how many unknowns there are or how many variables there are. So in the first problem, the long way to do it would be to take any powers of variables and expand them and then count 1, 2, 3, 4 variables. And then as you get the hang of it, you will just kind of count the powers. So x to the first power, 1 is implied, y to the second power, and then z to the first power, and then you add up the powers of the variables, and you get 1 plus 2 plus 1, which is a degree of 4. It's just coincidence that the coefficient is 4. And the next one, if you wrote it out, 2 cubed being 8, of course, and it's all about the variables anyway, so m to the fourth is 4 m's multiplied together, and then times an n. There are a total of 1 plus 4, or 5 unknowns, making the degree of this monomial the sum of those powers, which is 5. Look at the next one, pause if needed, think carefully about this example. Here, since dividing by 4 is the same thing as multiplying by 1/4, we see that this is not a monomial. So we would just say not a monomial, because since it isn't, we can't go by the rule of summing the variable's exponents to come up with the degree. It's not a monomial. In this class, for these polynomials, in this chapter, we will always have the same variable in a polynomial. So later on, we'll have like x to the third plus 2x squared minus 7. And there is a different rule for finding the degree of a polynomial. It's actually the sum of, or it's the highest degree among the individual monomial terms. So this degree is 3, this degree is 2, that one's 0, and 3 is the greatest, so that would be the degree of that polynomial. More to come on that. So for 7, that is like 7x to the 0 power, some variable to 0 power, because that's why it's not there. So then this has a degree of 0. Do not say that it has no degree. It does have a degree, and it is equal to 0. So now let's talk about polynomials. So they consist of monomials, or the sums of monomials. Their degree equals the highest or greatest degree among the monomial terms. So to go through this first example, I have a polynomial written in standard form. So the coefficient here of 6 is known as the leading coefficient. And then this power here, this 3, is the degree. As you can see, this monomial's degree is 2, then 1, then 0. So the degree of the polynomial, the collection of monomials, is going to equal the degree that is highest of all the monomial terms. Why is that? So if we do a little thought experiment off to the side here, and if I have this function f of x, and if I just have, let's say, x squared plus x plus 5, and then let's say I substitute in 10. So that would be 10 squared, or 100, and then just plus 10 and plus 5. Notice the x squared term is the largest of the three, so that is contributing the most to what the output is going to be characteristically. Let me substitute in a larger number, say 100. That squared is going to be 10,000. And we could see very quickly that this x squared term is trumping these other terms, especially the constant, which never changes. But even the x linear term, it fails to keep up. So that's why we only look at the monomial with the highest power to determine the degree of a polynomial. That's the highest degree among the individual monomial terms. That's the reason. And we'll learn later, that's the reason why the leading coefficient, which is always the one attached to the monomial with the highest degree, will determine whether the polynomial opens up or down, so to speak, in certain scenarios. More to come. So let's talk about classifying polynomials. This is just naming. So when it's of degree 0, that is a constant. Power of 1, it's linear. 2, it's quadratic, don't say parabolic. 3, cubic. 4, quartic. 5, quintic. You must remember and spell those correctly for full credit. Now, when talking about the number of terms, a single term is going to be monomial. 2 terms, binomial. And 3 terms is trinomial. The list goes on, but for our purposes, we'll stick to this list. So if I'm to classify this first example down here, I first want to make sure to view it in standard form. So that is in descending order of the powers. And now I look at the degree of each monomial. This one's 4, that one's 2, this one's 0. So the degree of the polynomial equals the highest degree among the monomial terms. So my degree is 4, and I have 3 terms. So what that means is I have a cubic, it's a degree of 4, so quartic, and then 3 terms, so trinomial. You always state the descriptor of the degree first. That's going to tell us that we could have a maximum of 4 real roots, and then trinomial means that we have 3 terms. So let's add and subtract, writing our answers in standard form. Please avoid the mistake of thinking that these parentheses at any point will mean multiplication. The operation between these two polynomials is addition. So really, the parentheses don't even need to be there. And so my strategy to keep my work to a minimum is to scan through these monomials and look for ones that have the same variables raised to the same powers, because those can add. So I see that the highest power is x cubed, so then I look at this and add it with that, and since the powers are the same, keep them the same and just operate on their coefficients. So 2 plus 1 gives me a total of 3x cubed. And then I go and look at the next highest power, which is squared. So that's a positive x squared and plus 5x squared. And then I go to the next highest power, which is linear. So I see a negative x over here I'm going to add that with a 7x over there for a total of plus 6x. And then lastly, I have constant, which is positive 9, added with a positive 4 for plus 13. So that's in standard form because of the descending order of the powers. And you would call that a cubic polynomial with 4 terms. So notice after 3 terms, we're just going to explicitly state the number rather than using one of the Greek words. So that would be a cubic polynomial with 4 terms. For the next one, careful that it's subtraction, so I recommend that you distribute that as a -1, changing all the signs of all the terms to the right, because you're subtracting them, which is adding their opposites. And now I go through the same process. I look for just the highest power. I see a degree of 2, so that's going to be a -2x plus 2x squared plus a -x squared, and that's going to give me a total of -3x squared. I go to the next highest power, so that's going to be linear. It's hanging out over here, and that's just adding a positive x, so it doesn't change signs. I already took care of that. And then lastly, I take the constant, so 3 plus 6 is 9. And that would be a quadratic trinomial. Quadratic because it has a degree of 2, and trinomial because it has 3 terms. Since this is the opening section of the chapter, I want us to use the graphing calculator to visualize what these polynomials can look like, as I demonstrated at the beginning of this lesson. So when you're describing it, you'll do so from left to right. That's how we do things numerically. That's how the number line works. And we want to identify increases and decreases, how many intersections with the x-axis, and how that corresponds with the number of real roots. And we'll dive deeper into each of these characteristics of the polynomial graphs as we go through the chapter. So for now, we just graph the polynomial function on a calculator. So you set this equal to y1, and you should get a graph that looks like the following. Something to that effect. Now, to describe the graph, we're just going to say that, well, from left to right, it increases, so it goes up. So right here it's going up, 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 like on a roller coaster, and then it's going to go down, and then it's going to go back up. So it goes up, then down, and it leaves the screen at the top, going up again. Now, that will mean a lot more to us later, but for now we're just kind of training ourselves to think of it left to right, and to imagine how it's increasing or decreasing as if we were riding along this curve on a roller coaster. The next thing we want to talk about is how it intersects the x-axis 3 times. We're no stranger to finding the roots of things, so we're going to just say 3 x-intercepts, so 3 times it crosses the x-axis. And that means there are 3 real roots. So that kind of gets the gist for now. And notice the degree is 3. And that corresponded to the number of real roots in this case. Later we'll find, let's say we have this as our graph. So that looks like a cubic as well. Let's say it is of some variety. But it only has 1 x-intercept, so then that would have 1 real root, and that means it would have 2 complex roots. We'll look at that later in the chapter.